Hello, students. So you may have noticed that the series that we got for the exponential generating function, we got this. Well, this is just a product of two very well-known series. Two pretty famous series here we have going on. So let's try to express this. What happens if we multiply these out? Well, let's see. I'd get 1 plus x squared plus, let's do one more term, dot, dot, dot. And here we'd get 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial. And the next one would be a minus, and so on. Okay, so this is the generating function that we got, the exponential generating function that we got for our derangements. So what we really are interested in is the coefficient of x to the n here. So let's sort of see what we would get. Like, for example, for the coefficient of x to the 0, I would just get 1, because the only way we could do that is a 1 and a 1. What we're getting is the convolution here. So for x to the 1, I guess let's start off with the 1x here. So we would get either a 1x and x times 1, or a 1 times minus 1. So what we're going to have here is we're going to have, let's see, 1 times x. Well, let's write it like this. Let's write it as x minus x for now. Okay, now for the next one, I'm going to write this as x squared minus x squared plus x squared over 2 factorial. For the next one, x cubed minus x cubed plus, okay, so I got this, the next one is x cubed over 2 factorial, and it'll be minus x cubed over 3 factorial, and so on and so forth here. Okay, well, let's see what I'm getting here exactly. Well, what this is this is going to be 1 plus, well, I could express each of these. We could see there's a pattern here, right? This is 2 factorial, this would be over 1 factorial, and this would be over 0 factorial. So I'm getting, if I pull out an x, 1 over 0 factorial minus 1 over 1 factorial. And this would be 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial. And if I pull out an x cubed, this would be a 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. And so on. So I can definitely see what the pattern is here, right? What's the pattern? I can get the coefficient of x to the n. The coefficient of x to the n, this is going to be this sum, which I'll just write as k equals 0 to the n of 1 over k factorial, and this is going to be times x to the n. So for example, the coefficient of x to the 1 is 1 over 1 factorial. Oh, and I also need a minus 1, so let's do minus 1 to the k, because I need each term to alternate. Okay, so now that should work. For example, when n is 1, I'm going to get, well, 1 over 1 factorial minus 1 over 1 over 0 factorial minus 1 over 1 factorial. And for example, when n is 3, what would I get? Well, I'd get exactly these 4 terms. I'd get positive 1 over 0 factorial, minus 1 over 1 factorial, positive 1 over 2 factorial, and then minus 1 over 3 factorial. So this is exactly what I have here. Okay. But remember, this was the formula for the exponential generating function. And what I have here looks like an ordinary generating function. So this isn't going to be compatible with what we had, right? Because this whole thing, this is equal to the sum from n equals 0 of this. So I need an n factorial. Otherwise, this is sort of not meaningful. So what could I do? Well, I could force it. Remember, I like to sometimes say that there's only 2 tricks in my lower level courses. And one thing is you're allowed to multiply by 1. So I'm just going to multiply by n factorial over n factorial. So what I have here now is this. The sum from k equals 0 to n of minus 1 to the k over k factorial times x to the n over n factorial. Okay, so now I know that this thing over here is equal to this thing over here, and the only way for these sequences to be the same is if, well, for the coefficients of each of the x to the n to be equal. And that must mean that dn is equal to this thing, which is n factorial times k equals 0 to n of minus 1 to the k over k factorial. And if you remember, this is the formula that we found earlier in the section on inclusion-exclusion for derangements. The non-recurrence formula, the one that just spits out the exact number for the number of derangements. And all we did in order to do that is multiply out these two things, and then we made sure that we expressed it as an exponential generating function by looking for the coefficient of x to the n over n factorial. Because, well, we knew that this was the exponential generating function for dn. And I mean, there's no real reason to do any examples here because we've done these in the section on inclusion-exclusion, but I guess just for fun, let's compute d2. We'd get 2 factorial. And what would this give me? Well, this would give me 1 over 1 factorial minus 1 over 2 factorial. And that would be 0, 1, 2. There we go. That's what this formula gives me because it starts at 0 and it ends at whatever n is. So if n is 2, this is what I would get. And of course, this is going to be 2, 1 minus 1 plus 1/2 is 1. And we know there's only one possible way to derange two objects, because if nothing's allowed to be in its original square, and the reds are sort of my rooks, well, the only thing that I can do is this. Okay, one position is going to work. And you could check for other numbers and as well. But this is very nice. This is another generating function proof. This is a proof of this formula. And the thing is we didn't even know that we were going to get this when we started. I might have gotten another formula involving derangement. So, you know, it not only allows us to prove things, it allows us to discover things once we know the generating function or the exponential generating function for a sequence, which is very exciting.